Improving Sports Performance Through Video Analysis by Ewan Ferguson and Ryan Kidd. We will be focusing on analyzing the hitting portion of baseball and explaining why video analysis will help improve your swing, among other things. The only thing that was known before video analysis was the way the ball reacted to the bat. Video analysis helps you dive deeper into the small little details like what angle your bat is at a certain point of your swing, or how fast your bat is traveling when it hits the ball, but it's pretty much to the extent used for those until about 3 or 4 years ago when a company named Blast started using crazy numbers to analyze every last detail of a baseball swing, starting from your hand positioning to all the way down to where your feet are at the point of contact. On this screen, you are looking at the 3D swing analysis from my last swing. You can see if I am on the proper swing plane when I start my swing and the point of contact I make. Those numbers on the side show the angle that my bat is at when I start, where my hands are, and if I stay on the correct swing plane. These are crazy ways that video analysis can improve baseball swings. Aside from the 3D analysis, there is the general analysis as well that can show you anywhere from stats from your bat speed, your hand speed, the acceleration you get, the time it takes you to make contact, and even the amount of power you're putting into the ball. To recap what you just saw, with extra numbers found that the app gives us, it tells us that I put 4.17 kilowatts of force into that baseball, which translates to 4,170 newtons of applied force. With the numbers that this gives us, and because of physics, we can calculate the distance the ball would travel without any air friction. So if the ball is traveling at an exit velocity of 97 miles per hour at a launch angle of 12 degrees after contact, and with a maximum height of 112 feet, with 2,500 RPM of backspin, the ball will travel just about 593 feet without any air friction. Again, another 3D analysis of the prior swing that's showing the start of the downswing, how long I stay on plane, and the point of impacts. To recap what you just saw with the last swing, I put 4.11 kilowatts of force, which translates to 4,110 newtons of applied force, with a 10-degree launch angle and a max of 100 feet with 2,800 RPM of backspin. The ball will travel 567 feet without any air friction. I collected all this data through an app called Blast Motion Baseball, which has been around for 3 years now, and it's just a little sensor that you put on the end of your bat to track your swings. Video analysis hasn't been used very much to improve hitting, but with the new app and the partnership with the 2018 World Series Championship Houston Astro player Carlos Correa, I'm sure we'll see more people start to use it. It shows a great help by breaking down every last detail to every last one of the swings to improve people's swing planes.
Carry the team, and there's still more in there.
High drive, right field. How far will it go? Majestic from Bellinger. Second for Bellinger, and a 6-2 lead for the...
Part 3. Analysis of a projectile motion. This is the data that we collected using Vernier's Logger Pro. As you can see, this is an image that we are using from the video using data tracking that is found from Vernier's Logger Pro technology. In the graph we have created with Vernier, the blue dots represent the inches that the ball has traveled off the bat, and the red dots represent the inches per second, so the velocity that the ball is traveling after contact. we see the blue dots at a gradual increase and then has a steep increase as the ball hits the bat and the velocity gets a lot higher, a lot quicker. Part 4. Force analysis of an object being launched vertically. This is Ryan throwing the ball vertically. This photo shows the points on the photo that we have plotted to input into our Vernier Logger Pro to create the graphs. From this graph we can see as the blue dots go up, the ball is thrown in the air, and as they come back down, the ball returns to its original point. And the red dots show us that it comes up and down in relatively the same line, give or take an inch or two due to human error. It also shows us how the force of gravity pulls it back down to its original point. This segment of the velocity time graph shows how the velocity slowly decreases as it reaches its peak and then increases back on its way down, and then on its way down it shows it how it has a negative acceleration because it is returning back to its point of zero. For the vertical throw, the mass of the baseball is 0.145 kilograms and the force of gravity is 0.145 times 9.81, which gives 1.421 newtons, which gives us our Fn for our force diagram, which gives us the force pushing up and pushing down on the baseball. The net force gives us our applied force, which is 1.545 newtons, and since friction is negligible in the air, it gives us a 0 newtons. Part 4. Force analysis of an object being launched horizontally. This is a photo of the horizontal launch with all the points on the graph shown on the photo. In this position time graph of the horizontal movement, we see the red line represent the position moving back away from the 0 point as he hits the ball and it rolls away from him, and the blue line represents how the point stays on the same flat surface the entire time. This velocity time graph represents the horizontal in inches per second. This shows how as it moves away, the velocity gradually gets bigger as the ball picks up speed. For the horizontal graph, we know that the mass of a baseball is 0.145 kilograms and the normal force is 1.422 newtons. To find the net force, we have to do the mass times the acceleration, which is 0.154 kilograms times 2.7 meters per second squared, which gives us 0.3915 newtons of net force. This gives us our force diagram. We have an applied force of 0.3915 newtons, and then we have the force of gravity of 1.422 newtons, and we have negligible friction, which means pretty much zero, so we put 0 newtons of friction. Part 4. Object being launched at angle to horizontal. This photo shows all the Vernier Logger Pro points that we will input onto our graph.
Looking at the position time graph here, the blue dots represent where the ball is at a certain point in time. So at 0.5 seconds, it's roughly 0.2 meters below where it started. Also, because the blue dots are a little further spread out at the end than how they were at the beginning, it shows that the ball is accelerating. Also, the average velocity of the ball is 2.7 meters per second. So just to back that up, looking at the velocity time graph, it shows that the velocity is increasing. The velocity of the ball is increasing.
The horizontal angle plane graph has a mass of 0.145 kilograms, an acceleration of 2.7 meters per second squared, a net force of 0.3915 newtons, a normal force of 1.422 newtons. For the force diagram, we see 1.422 newtons up, 0 newtons because the friction is negligible to the left, 0.3915 newtons to the right, and then 1.422 newtons down.